smart microgrid system. We call it shared system hybrida energi terbarukan. There are the three energy sources. It's a grid, photovoltaic, and then battery. From the previous research, conclude that we need additional energy source to that directly connect to the battery. Yes. So for expansion it fuel cell, and then we plan fuel cell and FJ 1 kilowatt that we have to attach in existing system. Fuel cell chosen because it has no pollutant product in it, and it's like a generator. So when fuel cell connect to the shed, we can use fuel cell as like generator. So we make the backup system. The existing smart microgrid system have a hybrid energy controller. Hybrid energy controller is the central management device that manages all operation of shed, like monitoring electricity or energy supply. Shed consists of 3 connection lines. It's AC1, AC2, DC. AC1 connect with photovoltaic that through grid-tie inverter supply AC electricity to AC1 that directly connect to AC load. And then grid connected to energy control via AC2 lines, and the battery via the batteries, it's like a fuse, connect to DC line. The battery has storage device, and the grid as backup power. The priority of energy supply, the first is photovoltaic because it directly connected to a solar, and then the battery, not the grid. The battery fulfill the demand if it can. Then the grid supply when the battery system in the low SOC. And then the new topology that we have designed is we attach the fuel cell on the DC line with the converter. The fuel cell is 10 FJ 1 kilowatt with OCV open circuit voltage 59 volt open. The type of fuel cell is open cathode and closed anode. DC converter that we use in this research is MPPT. We want to MPPT with maximum power point tracker can maximize the power produced from the fuel cell and prevent charge or over discharge from the battery. So no backflow from the energy control to fuel cell. Then after we already attach the fuel cell into the shed, the priority change when that fuel cell become the fourth priority and start only when the grid is down. So the priority scenario is when the grid mode is when the shed connect to the grid or PLN, perusahaan listrik negara, and then when idle mode is when the shed disconnect from the grid. So fuel cell change the grid. This operation management set in parameters that we set in a hybrid energy control system. If the generator power start, stop, and generator of the hybrid energy controller over 0.72 kilowatt, and then fuel cell will operate. In this scenario, it has a battery. When it's lower than 40%, then the fuel cell should start. And this is the scenario of the new scenario on the shelf. When load less than PV power, the PV can manage the demand. When cannot, battery supply. And when the parameter are met, the fuel cell connected should operate so fuel cell can supply shell. And this trade when the PV are down, like when there's no sun. When the parameter is met, then hybrid energy controller send generate signal to relay 1, then request indicator R1. So user have to start the manual operation of the fuel cell. This is the shaft that already operate, and its fuel cell and its control system, instrumentation and control. Nah, the experiment, when fuel cell connect to the battery pack, it's disconnected from the hybrid energy controller. So fuel cell supplying the battery 12 volt, 24 volt, 36 volt, and 48 volt. The result, given that when the voltage drop, more current applied. So in this current and what? So when more current supplied to the battery, then the power produced from the fuel cell higher, and the maximum power in this experiment. So when the lower voltage, we have more power in it. This when we connect to the hybrid energy controller, we connect to the shaft. The battery system at 47 voltage, and then the fuel cell at around 3 volt above the battery voltage. So because it have high voltage, they only produce 120 and 160 watt, because we already know about the IP curve. And then the charging experiment with the 3 different initial voltage, we want to know how the voltage of this battery. Then the result is given that the voltage of the battery still decreasing and drop, because when the fuel cell operate, the battery is still discharging, because the load 10 ampere and fuel cell only produce like around 3 ampere. So battery is still discharging in here, around 7 ampere. And we want to know the fluctuating load. In the hybrid energy control, we manage some fluctuating load. And here we start with 7 ampere. This MPPT out, and here this battery out, and then the inverter in. When the load are increasing, the battery supply follow it, but the fuel cell, it's stable in like 3.5 ampere, because the fuel cell follow MPPT performance, we know about the performance of the MPPT. It's different from the power in and power out. The high efficiency happens when at low voltage, because when the low voltage, more power produced. In this experiment, we want to know how high series habit and control responds to the parameter that we have set when it's a power limit experiment. So when the power from 0.6 we increasing until it reaches 0.772, the generic signal appear when like 200 seconds after the load access the parameters that we have set. So we start the fuel cell in here. The current supply the habit and efficiency control system. When we decrease the power until it's less than 0.48, the generic signal is off. So we have to shut down the fuel cell, and it's off in here, the supply. And this the SOC limit experiment. When the SOC made the 40%, the generic signal in that time it's on, and then we start the fuel cell. But because the fuel cell only produce power around 120 watt, but the load is more than like 10 ampere, it's around 500 watt. So the battery still discharging, and the load and the SOC never come to 80%. In design Microgrid analysis, we already know that our design is cannot to produce more power. Its MPP is 1 kilowatt. It's because the battery voltage in the 48 volt and the MPP is in the 28.8 volt. So we have to use the fuel cell with the higher OCV. We already use this OCV, but we can use the higher like 120 volt, or we apply the AC coupling design. So we use the inverter that can operate the fuel cell in this area. In the conclusion, the design that we have implemented on set to DC coupling with MPPT as its converter. The given result is fuel cell can only generate 120 until 160 watt power to the system. And to management operation that we have made by using AC generator startup function to count the fuel cell with SOC and the load parameter. The function through relay 1 when connected to LED 4 indicator. SOC limit is 40% and load power limit is 0.72 kilowatt. On the analysis, we found that with battery 40x volt and the fuel cell with OCV 59 volt, made that MPPT can operate fuel cell to its MPP. It's 20x.x. Then only can generate 120 and 160 watts. Then this coupling method made the fuel cell become the stable energy source that supply power according